We have another question on the board. Let's look at this diagram. Look at the diagram closely. Okay. So observe the diagram closely. Alright, observe it closely. We can see a box. It is anchored by 3 wires or 3 cables. Of course, that block or the box will have a weight. It is anchored at point A. Okay, and that is the x-axis acting over there. The z-axis is acting this other way, and the y-axis is upwards. So the cables are cable AB, cable AC, and cable AD. Alright, so that is it. Take note of the diagram. Take note of the diagram. Okay, observe the diagram closely, please. Observe the diagram. Okay, ensure you have a book and pen as I'm solving. You work together with me. A crate is supported by 3 cables as shown. Determine the weight of the cable, knowing that the tension in cable AB is 750 Newton. Now this is the free body diagram to that question. The free body diagram, you draw your free body diagram, FBD. Okay, this is it. This is the simple free body diagram to that question. This is the free body diagram. Okay, so that is the free body diagram to that question. That is it. Y-axis, x-axis, and z. Okay, so the weight of the body will act vertically downwards. That's the weight of the block. Okay, that's what they say we should find. We should determine the weight of the crate. So the weight will act downwards. Then this is cable AB. Cable AB is this one. This is the unit vector. This one now is the vector TAB. Then we have the vector TAC acting along here, and this is the unit vector AC. Then for cable AD, this is the vector TAD, and that one is unit vector. These are the dimensions given to us. This is x. On the x-axis we have the I coordinates. On the y-axis I have the j coordinates. On the z-axis I have the k coordinates. Okay, so let's look at that. Now the next thing I'll look at now is to take the resultant of all the forces. Take resultant of all the forces acting on that system, and I'll be having. Okay, so I say take the resultant. Take the resultant of all the forces, and this will give me R equals to sigma F, which is equals to, first one there is tension along AB. Okay, tension along AB plus tension along AC. Okay, plus tension along AD, then plus the weight. Alright, so I call this one equation 1. Alright, so this is it. Summation of the forces: tension along AB, tension along AC, then tension along AD, and then my weights. I'll call this weights, make it a vector. Vector. That arrowhead shows you that these are vectors. The arrowhead shows you they are vectors. Okay. Now the next one, I'll say consider cable AB. If I consider cable AB, I have that RAB will be equal to, come back to AB, cable AB. Okay, this point is point A, and then this is point B. So I'll look for a way I'll move here until I get to point B. So this will be, so I come back again. Okay, so let's move. If I move from point A going upwards, this is the distance. Going up like this is 60 J. Okay, this is the distance. So if I'm going up now, this is J. J up is what? Going up like this is positive J. Coming like this is positive K. Going like this is positive I. So if I move now, this is 60 J going upwards, 60 J. Then I'll move to this point. I'll move from here now. From here I move. This is minus 27K. Since it is going like this, coming like this is K plus K. So going like this now, when I get to this point, I'll move. This is minus 27K until finally I get to point B. To be minus 36I. Okay, so let's move again. Going up 60 plus 60J, then I'll move like this to be minus 27K. Then I'll go from that point, I'll go to point B, which is minus 36I. I is coming like this, but this one is going like this. It will be minus 36I. Then K is coming like this, but this other distance is moving like this. 27 is coming like this now, so you move like this, minus 27K, and I go like this, minus 36I. That is 36 minus 36I. So let's take that quickly. So this will give me 60J, then 60J going up, 60J, then I move like this. That is moving like this is minus 27K, then minus 27K. When I get to this point, I'll then move to point B, minus 36I, because this is I as it's going against it now. Move like this, minus 36I. So arranging it properly now, I'll be having that RAB is equals to minus 36I plus 60J minus 27K. Okay. So this is the position vector. Now the next thing I'll look at now is find the unit vector, the modulus. The modulus RAB equals to square root of minus 36 all square plus 60 all square plus minus 27 raised to the power of 2. Alright, so this now equals to the square root of give me 1296 plus 60 square will give me 3600 plus 27 square to give me 729. So when I add it now, I'll have square root of give me square root of 5625. That means that RAB modulus equals to the square root of this now is square root of that will give me square root of this will give me 75. Okay, so that is it. So I have the modulus as 75. Then this is the position vector, minus 36I plus 60J and 27K. So that means now my unit vector lambda AB will be the position vector over the modulus of the vector. So that is lambda AB will be equal to the position vector is minus 36I plus 60J minus 27K divided by 75. If I split it now, I have lambda AB is equals to minus 36 divided by 75I plus 60 divided by 75J minus 27 divided by 75K. Alright, so if I now split this, but if I divide this now, I'll have so if I divide, I'll be having minus 0.48I, this is lambda AB, minus 0.48I. Then remember, this is what I'm dividing. I divide by this, I have that. Then divide this and divide this other one, I'll be having this is plus 0.8J minus 0.36K. Okay, so this is it, lambda AB. So then I can then look for vector TAB, which is equals to tension TAB lambda AB. Okay, all right, so that is it. Okay. Now come back to this question. They said knowing that the tension in cable AB is 750 Newton, so the original tension force acting in cable AB is 750 Newton. That is the original tension force that acts along cable AB. Okay, all right, not this one is the vector force. So the original tension force acting along cable AB is 750 Newton. So that means that TAB vector TAB will be equals to 750 multiplied by, put the value of the unit vector there, that is minus 0.48 I plus 0.8 J minus 0.36 K. Alright, now if I multiply that by means of expansion, I'll have, so this will give me minus 360 I plus 600 J, and then this one will give me minus 270 K. Alright, so this is what I'm having. Okay, now of which I can call this equation 2. Okay, call this equation 2. Alright, that is minus 360I plus 600J minus 270K. Call that equation 2. This is equation 1. Okay, this is equation 1. I call this equation 2. Now I say consider cable AC. Consider cable AC. That will be okay. So we come back again to the free body diagram. Now let's do this. Let's do this from A to C. Come on, let's go. Now this is from A. You move from here, you go stop here. From A, you move here, then you come down to C. That's all. Now let's go. Going up, that is plus 60. This is it. This is the distance. Plus 60J. You come down here. That is plus 32K. Okay. You move up. Plus 60J. That is going up like this. Plus 60J. You come down. This is the distance, 32. Come down like this. Plus 32K. So we go again. Plus 60J. Plus 60J. Then you come down like this. Plus 32K. Okay. So RAC. Vector RAC. Position vector RAC will be equals to that 60J plus 32K. Okay, that is it. From here we moving up, that is 60J, going up like this, 60J, and then we come down to point C, 32K. Okay, so take note of that. Move 60J, come down to C, 32K. All right. Okay, so we then you can find the modulus of the vector RAC. The modulus of vector RAC will be equal to the square root of 60 raised to the power of 2 plus 32 all raised to the power 2. So it equals to the square root of 3600 plus 32 square will give me 1024. So this now will be the square root. So if you give me square root of if I add them, I'll have, this is square root of 4624. Okay, the square root of my answer now will be, so RAC is equals to 68. Okay, RAC is equals to 68. So this now, I see my position, my unit vector lambda AC is the position vector RAC over the modulus. Okay, so the unit vector is equals to the position vector over the modulus, which is my position vector is 60j plus 32k. Okay, so take note of that. This is it. Alright, so I have 60j plus 32k divided by 68. So that means that lambda AC will be equals to, if I split it, 60 over 68j plus 32 over 68k. Okay, so lambda AC will be equal to, if I divide that now, I'll be having, this will give me 0.882j plus 0.471k. Okay, so that is 0.882j plus 0.471k. Alright, so I can then continue now. This is tension force AC will be equals to TAC lambda AC. Okay, so the vector TAC will be the original tension force times the unit vector. So that will give me, if I substitute now, I'll be having, so by means of substitution, I have tension TAC, okay, equals to TAC times lambda AC 0.882j plus 0.471k. So if I add them now, I have 0.882 TACJ plus 0.471 TACK. That's the tension force AC. So I can call this one equation 3. Okay, so that's it. When I expand it, I'll have this 0.882 TACJ plus 0.471 TACK. Alright, so I say consider cable AD. Consider cable AD. So I come back to the free body diagram. Let's look at this free body diagram. Now, consider cable AD. I'll look for a way I can navigate through from point A to point D. Okay, now let's move. If I move here, going from A, go upwards, with respect to this distance, let's move from here like this, is plus 60j. When I get to this point, I'll move again. That will be minus 27k. Then I move down to this point, plus 40i. That's the 40 there. Okay, so let's move again. Go up from A, I go up like this. That is plus 60j. Go up plus 60j. Then move like this. This is 27, right? Move like this. This coming here is plus I. Move like this from here. Minus 27k. If you're coming like this, it's plus k. So move like this, minus 27k. Then come like this, plus 40i. Okay. So take notes. So I move up, plus 60j. Then I move like this. That is minus 27k. And I come like this, plus 40i. Alright, so take note. I repeat again. Going up, plus 60j. You go like this. That is minus 27. Minus 27k. K is coming like this. So if you are going opposite, it is negative. Minus 27k. Then I come down like this. It's going with respect to I. So I come down like this, plus 40i. I stop at point D. Okay, so that is it. So it implies that arrow AD will be equals to, as the unit, the position vector arrow AD will be 60j. Then I said you go this other way, that's minus 27k. Until finally you come down to D, plus 40i. Okay, so if I read it properly now, that will be 40i plus 60j minus 27k. This is RAD unit position vector rather. Now the modulus of the vector now will be modulus RAD give me, okay, so the modulus of this vector, the modulus of the vector is 40 all square plus 60 square plus minus 27 raised to the power of 2. Okay, so this now is equal to square root of 40 square is 1600, 60 square is 3600 plus 729. When I square this one, I have 729. Okay, so when I add them now, I'll be having the square root of 5929. So finding the square root now, I have, so this will give me 77. Okay, this is RAD modulus. Okay, so the modulus of RAD is that. Now I find the unit vector lambda AD will be equals to position vector RAD divided by the modulus of the vector. So if I do that now, I'll be having unit vector lambda AD is equal to the position vector is 40i plus 60j minus 27k. Okay, so divided by 77. So I'll be having lambda AD is equals to 40 divided by 77i plus 60 divided by 77j minus 27 divided by 77k. So the lambda AD will give me, if I divide that now, we're having 0.519i plus, this other one will give me 0.779j. Which other one will give me, minus 0.351k. Alright, so that's what I'm having. When I use my calculator, using a scientific calculator, you get that quickly. Okay, so that's when you divide. Alright, so the next thing I'll look for now is the vector TAD. Vector force TAD will be equals to force TAD lambda AD. Okay, TAD lambda AD. That will be, so this now will be vector TAD equals to TAD times lambda AD is 0.519i plus 0.779j minus 0.351k. So if I multiply now, this will give me 0.519 TAD I plus 0.779 TADJ minus 0.351 TADK. Okay, as the force TAD. So the vector force TAD is equals to this. Alright, which I can call this one equation 4. Now then go back to that diagram. Go back to the diagram. Now we have the weight acting vertically downwards in the free body diagram. We observe that the weight is acting vertically downwards, that's W. Okay, so since it's acting vertically downwards, this is also a vector. Take this as a vector, it's a vector W. So it means you say consider the weight of the crate at point A. So if I consider the weight of the crate at point A, this is the vector W equals to minus WJ minus WJ. Okay, consider the weight of crate at A minus WJ, which I can call this one equation 5. I can call that equation 5. So I'll substitute. I hope you know the reason why it's negative, because the weight is acting vertically downwards, so it will be negative J. So substitute equation 2, equation 3, equation 4, and equation 5 into equation 1. Right? Recall that equation 1 is R equals to sigma F, which is TAB tension plus TAC tension plus the vector TAD plus the weight, vector weight, okay, vector of the weight. So this now will be sigma F equals to, if I substitute the value of TAB, vector TAB, that will give me, the vector for TAB will give me, okay, so this will give me minus 360 I plus 600 J, okay, is minus 270 K, okay, plus I put that of TAC, that is equation 3, and this is equation 3. I put equation 3 inside that. I'll be having an open bracket 0.882 TACJ plus 0.471 TACK plus put equation 4 into the equation. This is equation 4. Put it there. So I have 0.519 TADI plus 0.779 TADJ minus 0.351 TADK plus the weight is minus WJ. Okay, so I'll then arrange them properly in both I, J, and K coordinates. So let's take the first I coordinate there. The first I coordinate is minus 360 I. So this now will be minus 360. Then take the next I coordinate. Okay, there's no I coordinate here. There's an I coordinate here. This is plus 0.519 TAD. Okay. I. Okay. The next I coordinate, no other I coordinate. So I can call this. This is I plus. I come over here. J coordinates. This is J. This is J. This is J. And this is J. So I take the first J coordinate. That is 0.882 TAC. Then, sorry, the first J coordinate is 600. That was a mistake, please. 600 is the first J coordinate. 600J. That is 600 plus, that is this. And I take the next one. This one is 0.882 TAC. Okay, that's this. And I come back, I take this other one plus 0.779 TAD. And I take this one minus WJ. Okay, and I take the K coordinate minus 270 plus, you have minus 270. Then I take this K coordinate plus 0.471 TAC. And this is K coordinate as well, minus 0.351 TAD. K. Alright. So this is what I'm having as my sigma F. So the summation of forces now, this is on the I-axis, it's on the J-axis, and on the K-axis, okay? On the I coordinates, or the mistake, I coordinate, J coordinate, and K coordinate, okay? So now we know that sigma F is equals to sigma Fx I coordinates plus sigma Fy J coordinates plus sigma Fz K coordinates. That is when you are looking at forces in 3 dimensions, 3-dimensional force system. So that means that sigma Fx will be equals to, if you compare the both equation, compare this to the whole of this. Sigma Fs is this, sigma Fy is the whole of this, and sigma Fz is this. So we'll be having minus 360 plus 0.519 TAD as sigma Fs. And sigma Fy will be equals to 600 plus 0.882 TAC plus 0.779 TAD minus W. And sigma Fz will be equals to minus 270 plus 0.471 TAC minus 0.351 TAD. Alright, so this is what I'm having, minus 360. Then you come over there, take the next, then you finally take the last one. So that is it. Okay. Alright. So I'll then apply equilibrium conditions. Applying equilibrium conditions there. Equilibrium conditions now. States that sigma Fx is equals to 0, sigma Fy is 0, and that sigma Fz is 0. Okay, so I'll equate this to 0, equate this to 0, equate this to 0. For the body to be in a static equilibrium, the summation of forces on the x-axis will be 0, summation of forces on the y-axis will be 0, summation of forces on the z-axis will be 0 as well. So these equations now will change, and I'll be having so if sigma Fx is 0, it implies that I'm having minus 360 plus 0.519 TAD. I can call this equation 6. And if sigma Fy is 0, I'll be having 600 plus 0.882 TAC plus 0.779 TAD minus W, of which I can call this one equation 7. Okay, and also if sigma Fz, sorry, I'm supposed to equate it to 0. Equate them to 0, please. Equate it to 0 and equate this to 0. Okay, and then if equate this to 0, if sigma Fz is 0, that means that also that of sigma Fz will be influenced. That is, it means we'll be having minus 270 plus 0.471 TAC minus 0.351 TAD is equals to 0. Okay. Alright, so that's what I'll be having. 0.471 TAC minus 0.351 TAD equals to 0. Now I can call this one, I can call this equation 8. Alright? So I'll start from equation 6 and see what I'll be getting there. Start from equation 6. You say from equation 6, I'll bring equation 6 out. I'm having minus 360 plus 0.519 TAD is equivalent to 0. If I take this minus 360 over here, I'll have 0.519 TAD is equals to 360. So I'll divide by the coefficient of TAD, that is tension AD, will be equals to 360 divided by 0.519. So if I divide it, that I'll have, so this will give me 693.64 Newton. Okay, that is tension in AD. So I've gotten the tension in the rope AD. As tension in the rope AD, 693.64. Tension in the cable AD, 693.64. I'll then substitute it into equation 8. You say substitute TAD equals to 693.64 Newton into equation 8. You substitute that into equation 8. Now equation 8 now will change to, that is minus 270 plus 0.471 TAC minus 0.351. Open bracket. In case of this TAD, I write this value, which is 693.64 is equal to 0. Alright? So I'll be having minus 270 plus 0.471 TAC minus, if I multiply this now, I'll be having I'll give me 243.46 equals to 0. Okay, so then I'll combine this. That's like saying minus 270 minus 243.46 plus 0.471 TAC is equals to 0. Okay, so this one minus this one will give me, this will give me minus 513.46. okay, plus 0.471 TAC is equals to 0. So if I carry this one over here now, I have 0.471 TAC equals to 513.46. So tension in AC will be equals to 513.46 divided by 0.471. Okay, so if I divide it now, divide that by 0.471, I'll have, so this will give me 1090.15 Newton. So tension along the cable AC is 1090.15 Newton. When you divide with your scientific calculator, you have this. Okay, so take note of that for all that we have solved there. Okay, so observe everything we did there. After substituting, we solved and then we arrived at this. Finally, you divide and you have a 1090.15 Newton. So I say substitute TAD equals to 693.64 Newton, and TAC equals to 1090.15 Newton into equation 7. Equation 7 now, write down equation 7, that is 600 plus 0.882 TAC plus 0.779 TAD minus W equals to 0. So if I put the values here, I'll be having 600 plus 0.882 multiplied by the value of TLC is 1090.15, okay, plus 0.779. The value of TOD is this. Value of TOD is this. That's 693.64 minus W equals to 0. Okay, so now this will give me 600 plus, if I multiply this, I'll be having, so give me 961.51 plus, if I multiply this other one, I'll have so give me 540.35 minus W equals to 0. Okay, that's when I multiply this by this, I have this, and this times this, I'll have this one. Okay, so if I add them now, I'll be having 2101.86 minus W is equals to 0. So when I add all of them here, I'll be having 2101.86, 2101.86 minus W. Now if I carry this minus W over to this side of the equation, once you cross the equality sign, change it to plus. That's 2101.86 equals to W. Therefore, W is equals to 2101.86 Newton. Okay, this is the weight of the crate. The weight of the crate is 2101.86. So the weight of the crate, is 2101.86 Newton. All right, so we have solved it. We have solved that question. Okay, we have solved the question. So just observe everything that we did, and ensure you have a book and a pen, copying, taking notes. Right. Okay. Right. This was the free body diagram. That was the free body diagram. This is it. This was the free body diagram. Okay. So we have come to the end of the lesson. Okay. Come to the end of this question. Okay. Thank you. God bless you. Bye for now.